Thank you. So this is a joint work with a group that you can see the name here, coordinated by Patrizio. Okay, maybe I will use this. So coordinated by Patrizio Neff, and I will talk about some numerical simulations on a model that is called relaxed micromorphic model. So we want to describe the macroscopic behavior of a micromorphic medium with particular substructures, and to do so we start presenting the relaxed micromorphic continuum medium recently proposed, and we study for this medium wave propagation in the considered relaxed medium, as well as in the classical micromorphic medium. In the same way, we will show some results also for Cossera and second-grade materials, as seen as a degenerate case of the previous two. We will see that we can show band gaps only for in the relaxed model, only for non-vanished Cossera couple modulus, and this is the main result of this presentation. So the kinematics that is used is that for a micromorphic medium, in which you see the classical potatoes of the reference configuration, the present one, potatoes, and the placement that goes from capital X to X. But in a micromorphic model, every point in the reference configuration corresponds to a certain representative volume element that can displaced somehow, and in a general micromorphic model, this displacement can be not only rigid, but can be inside some deformation evaluated by this tensor P. So we have the classical map P that represents the classical placements. So we have the classical placement key, and we have another placement that is the microscopic one, key prime, and the tensor P that describes the independent motion of the substructure. And this substructure, as I have already remarked, it can not only rotate but also deformed. In the classical Mindlin-Hennigan micromorphic model, the basic constitutive variables are those that you can see in the first line, and the energy of the Mindlin-Hennigan micromorphic model, in the case of linear centrosymmetric materials, is of this type. For this energy, well-Posner's results are established in the literature, and these results are based on uniform positivity. For the relaxed micromorphic model on which this presentation is based, on this work is based, we particularize the previous this tensor E equal to 0, and the basic constitutive variables now it is not anymore the gradient of P as in the classical case, but the curl of P, because and this curl of P is also called dislocation density tensor, and this is the model on which connected to to the model presented by Samuel Forrest, Professor Forrest. So, and the energy of the relaxed micromorphic model can be written in this way. And for this relaxed model, the well-Poisson results are recently proved by this work. For the isotropic case, the energy can be written in this way. We can say that when the Cossera modulus, couple modulus, mu c is vanishing, then the Cauchy stress tensor is symmetric. In this case, this is a good choice for the description of a huge variety of engineering microstructured materials, but it is not enough to describe those metamaterials that exhibit band gaps. And we will show now that the Cossera couple modulus mu c is the responsible of the onset of band gaps in this relaxed media. So the relaxed micromorphic isotropic energy is the first one. In the second case, we have the classical one. You can see that the difference is just in the last term, in which instead of the gradient of p squared, we have the curl of p squared. And a relation now between the relaxed micromorphic isotropic energy that is shown now on the top side, and the energy for the Cossera is shown here as the limit case of the parameter mu h going to infinity. You see that in the minimization process, if you put mu h to the infinite, the symmetric part of P should be 0, and you have only rotation of the microstructure, because this is a linear case. So now if you take the relaxed micromorphic energy and simultaneously take a very high value of mu e and mu c, you see that the symmetric part, the symmetric part and the skew symmetric part of the gradient of u and of p will be equal, and we have a second gradient energy as a degenerate case, limit case of the classical one. So to find the dispersion relation, we start with an action, the kinetic energy of which is shown, and for which the internal energy W is one of the previously shown. So we perform the variation, and after a suitable number of integration by parts and imposing a variation of the fundamental kinematical fields to be arbitrary, one gets the equations of motion in the strong form for the considered material depending upon the internal energy that we can choose. The equations for the relaxed medium is this one. These are the first two, and the equation for the classical micromorphic medium are the last two. The difference you see just in the last term of the second equations. We have the curl of the curl in the relaxed medium, and we have the Laplacian operator in the second medium. We will study wave propagation in the following case. So the relaxed micromorphic model, the classical micromorphic model, the Cossera model as seen as a limit case of the relaxed model, and the second gradient model as seen as the limit case of the classical model. We will show that the relaxed model with non-vanishing couple modulus is the only continuum model among the previous ones, which is suitable to describe band gaps. To do this, we consider a simplified case in which all the unknown fields depends only upon one variable, and so following the famous paper of Mindlin, we consider this set of variable and obtain the following set of equations for the relaxed, and this is for the relaxed. These are the equations for the relaxed medium, and these are the equations for the classical one. In this equation, we have used these characteristic speeds and frequency. If we set now, if we define this V1, V2, and V3, we can consider a plane wave solution and arrive to the following dispersion relations. The first two lines are the dispersion relations for the relaxed medium. The first line and the last line are the dispersion relation for the classical medium, where the matrices A1, A2, A3 are this one, and B1, B2, B3 are this one. I do not have time to discuss this. But the results for the dispersion relation, we have shown the results for this dispersion relation in the following way. We have we can see the set of partial differential equations that can be seen as into three groups, so that on the left hand side we see the dispersion relation for the uncoupled waves, in the center for longitudinal waves, and on the right hand side we have the transverse waves. This is the dispersion curve for the relaxed model. So for the relaxed model with mu c equal to 0, and we cannot see any band gap because, you can see that for every frequency we have a solution in terms of wave number. On the x side, on the horizontal side, we have wave number. In the y side, we have frequency. And on the other hand, if we take mu c different from 0, we can show band gaps in all of these three pictures of the dispersion relation. Then we can see dispersion curves, the analogous dispersion curves for the Cosseram media, if we let mu h, as I have told you before, in the relaxed model. And the same work can be done for the classical micromorphic model. You see that here it seems band gap, but only for this part of the equation, but we have to consider all the three pictures of the dispersion relation, and also the second gradient dispersion relation as seen as the limit case of the classical one when mu e and mu c go to infinity. So some conclusion that is better that I read from here because that is very difficult to read. So the relaxed micromorphic model has 6 parameters, and only the term the square of the curl appears in the strain energy, and is fully able to describe the main features of the mechanical behavior of micromorphic continua. First of all, for what concerns the possibility of describing the presence of band gaps. Then from this model one can reduce one parameter and arrive to a 5 parameters model with mu c equal to 0. This simplified model produces asymmetric Cauchy force stress tensor that is sometimes useful, but this model is not able to see band gaps. The Cosseram model is obtained as a degenerate case of the proposed relaxed model, letting mu h go into infinity. The Cosseram model is not able to describe band gaps, as we have seen, but introduces non-symmetric Cauchy stress tensor. And moreover, do not introduce a non-symmetric Cauchy stress tensor. The classical continuum models with 6 parameters parameters, and the gradient of p squared in the strain energy is also shown, and it is qualitatively equivalent to the full 18 parameters Mindlin-Hennig and micromorphic continuum model, from a qualitative point of view, of course. This is true since the classical model is controlling all the kinematical fields of the full model, and it is uniformly pointwise. And the classical continuum model is not able to forecast band gaps. Second gradient theories can be obtained as a limit case of the classical one, letting mu e and mu c go into infinity, and these theories again are not able to account the presence of band gaps. So thank you.
Thank you.
Okay, on the boundary you mean if I excite the medium on the boundary in the frequency range. In the frequency range. No, I don't have an answer. We should see better these results. I'm sorry.
Another question is when you look at the Placidi theory,
yeah.
you always complete Placidi theory. Yes, there is 6 parameters.
Yeah.
But if you consider just a moment, when you consider the Placidi model where the total stress is 0, there is also a band gap there.
No.
Yes.
Not in this case. We have seen.
No, but I mean a particular case of Placidi model, when you put 2 other parameters to 0, then you will reduce
which parameters? Maybe
it's possible for existence of coupled stress. So
sorry.
when you have antisymmetric stress tensor,
Yeah.
0 coupled stress, it means that nothing depends on the
But in the classical, you mean this first one? With this gradient of p squared, you cannot have band gaps because.
Mentioning a ceramic which doesn't react to the gradient of the rotation. You may imagine this. It's called, well, we call it reduced ceramic. So it's a particular case, and it does have a band gap.
It does? Do you have the reference?
Yes, I know because I work with it.
Okay.
I should clarify that point. In this model, you cannot consider the reduced Cordova model of issues. You cannot get it by just putting some parameters here equal to 0.
It's not a particular case.
No, it's not a particular case. So it's both of you are right. Speaking about different problems having also a name of Cordova model.
Okay.
Okay, last question. This in the meantime. Can you give some physical reason why for some cases you have band gaps and why for other cases you don't have?
This I would like to answer in a comprehensive way to this question, because if I would answer, I mean, if I know this, maybe I could also find a micro. I could also project, design a metamaterial with this process, with this characteristic, and I mean, this is the target of this work, to find the reason. Sorry? Only elastic, yes.
Okay, so thank you again.